Hello, everyone, and welcome to the last Coffee with Caleffi of 24. This has been our biggest year ever for Coffee with Caleffi, so that's been really fun. And we're very excited about the topic that we have today because I think that this really is a cool topic that bridges what we kind of internally have conversations about. What is sustainability? What is resiliency? And where do they meet? And I think military applications are kind of a cool way to show this energy efficiency target from a lot of different perspectives. And Nicole Harvey is going to go through some of the slides to show the data behind some of these projects as we go through today. So I'll go through a couple housekeeping slides and then we'll turn it over to Nicole. So if you're having issues with the audio, you probably can't hear me anyway, but if you can read this, probably easier to just close GoToWebinar and reopen it. We will send a copy of today's presentation. If you'd like that, hit yes in the post-webinar survey, and then we'll put this up on YouTube as soon as we can as well, if you want to send it to a colleague or something like that. If you can use these in your jurisdiction, check with whoever's in charge in your zip code or with your credential body or whoever that would be. We will send a certificate of attendance that has the date, agenda items, and things like that. So if you can submit that, hit yes in the survey as well there. Hydronics 34 is up and is our most recent hard copy. We actually have Hydronics 35. I'll put it in the chat as we get rolling here. Is available on hydronics.caleffi.com right now, and we're just finalizing the hard copy for that for the PDF and the print version that we'll mail. So keep an eye out for that if you're a subscriber, or you can subscribe with that link. And then one of the things that we wanted to do, we've been doing this the last couple months, is kind of a Coffee with Caleffi shout out. So one thing that we'll talk about a little bit more with the introduction, but the AEE, the Association of Energy Engineers, has a cool mentor program. So you can sign up to be a mentor or a mentee. That is open now. So you have to be a member of the group. I've got the link there that I can put into the chat as well. But this is kind of a cool way to learn more about the industry, and of these types of programs that I've seen industry-wide, this one looks like it has a nice structure to it. So it's not just a, hey, here's an email address of somebody and hope that goes well. It seems like they've got a pretty good structure, and you can kind of tell by all the deadlines there that they are taking that seriously, and it's going to be a good use of your time. So we'll have a little bit more about that in a second. And then, so now we'll welcome Nicole Harvey. So she is a senior building systems research engineer at Pacific Northwest National Laboratory located in Bozeman. She is also the president of her local AEE chapter, the Big Sky chapter. So that was a passion project of hers we wanted to mention at the beginning. We are very excited to have Nicole do the presentation today. This is something that's been a few years in the making that we've been talking about, trying to find some presentation that would work here. And we're just very happy to have Nicole as our expert panelist today. I'm going to turn it over to you, and then I'll be back on to do the polls, I guess, immediately. So maybe I'll just stay on for that. But welcome, Nicole.
Yeah, sounds good. Thank you so much for the introduction. And I'm really happy to be here and talk to you guys about heat pumps in military applications, and then also kind of touch on a unique case study today that I did in grad school. So I'm going to start off today with a couple of polls. I just want to get a feel for how familiar people in the audience are with the United States Army, and then also with ground source heat pumps. So our first poll today is, have you worked on projects with the US Army? Yes or no?
So I've got that open now. You probably won't be able to see these results as they come in, but we'll give it a few seconds. Did you work on projects yourself with the Army in grad school, or is this something that as you moved into the lab?
Yeah, this has been something since I've moved into the lab. I really didn't have any experience with DoD or government before working with the lab. And then just given the sector of the lab that I was kind of put in when I was hired, my direct supervisor does a lot of work for the Army. And so that's just kind of correlated into a lot of direct work with the Army. And then the DoD, I also didn't describe, there's going to be a lot of acronyms today with the military, in case anyone does not know that. DoD is Department of Defense. I will try and remember to say what these acronyms stand for, but please, Max, if somebody drops in the chat, feel free to interrupt so that I can clarify what those acronyms are.
Sounds good. So we had a 35% said yes. So that's
Okay,
higher than
nice. That's
what.
pretty good.
So yeah, that's
Yeah.
interesting. So I'll share that with the group. Okay. And then I think we've got another one on the next slide as well.
Yes. The next one is have you installed or designed systems with ground source heat pumps before?
Okay, so I'll
And
launch that one.
yeah, just to give a little background, I guess, for me on ground source heat pumps, my dad is a plumbing contractor and he installed uh, quite a few ground source heat pumps in his time um, when he was working. And so I did some graduate research on a system that he installed at his house, which I'll touch on in today's presentation. And that's kind of how I got started in the ground source heat pump world and have been fortunate enough to continue that work at the lab now.
Yeah, very cool. It's nice to have the practical background to kind of see like all right, that that will that fit into that mechanical room? Is that it's gonna be
Right.
a good idea or not? Okay, so we had a 43% said yes,
Okay.
57% said no. I think that our just to complement our audience, I think our audience skews pretty technical and pretty industry technology forward. So it's probably
Awesome.
skewed a little bit in that way, but always nice to see what the audience of the day is.
Yeah. Okay, thank you guys so much for that input. So I wanted to start today off just by kind of giving like a high level overview of the Army. It's going to go back and forth the presentation today a little bit between the DoD, Department of Defense as a whole, and the United States Army. Most of the work that I do at the Pacific Northwest National Lab is for the Army. And I did want to clarify a lot of the studies today are not studies that we conducted at the lab. They're just studies that have been kind of conducted in general at the Army. So to get into information about the Army, it's the oldest and largest branch of the United States military, and their mission is to deploy, fight, and win the nation's wars by providing ready, prompt, and sustained land dominance by Army forces across the full spectrum of conflicts. And the Army covers more than 450 permanent installations in the continental United States. CONUS is the Army acronym for Continental United States. So why this presentation is primarily focused on the Army today is the Army has a lot of physical installations in the United States. So these physical installations, they're kind of like small cities. They have their own housing, they have their own commercial spaces, gas stations, grocery stores. At least the large Army bases do. They also range to as small as like 1 to 2 buildings for the Army Reserve, and then up to those small cities for things like the major military bases. And so ground source heat pumps are very applicable to the Army because they have a lot of energy that is being consumed at the building level. So to get into how the DoD and Army consume energy as a whole, the Department of Defense is the largest single energy consumer, both in the United States and among the federal government. So this is a huge area and opportunity to help reduce energy consumption just in the United States as a whole. And then as part of the greater DoD, the Army counts for about 40% of installation energy. And here, this image, they have operational energy and then installation energy. The difference here is that operational energy is the energy required for training, moving, and sustaining military forces and weapons platforms. So this is like transportation and operations energy. And then installation energy consists of the energy needed to power fixed installations and enduring locations, as well as non-tactical vehicles. So that's the energy that my work primarily focuses on, is reducing that. And then the installation energy consumption mix. So this is the energy that's consumed at those installations. I also don't think I touched on installations. So to touch on that really quick, the Army calls their military bases, or at least in my line of work, we refer to them as installations. So an installation is going to be something like Fort Gordon or Fort Johnson. That is an Army installation, just so everyone is on the same page and knows what I'm talking about. So here you can see that the installation energy consumption mix very closely mirrors that of the commercial sector, with most of the energy being consumed from electricity, but there's also pretty heavily natural gas consumption on these bases as well. So in the Army, the mission is the priority. This is something that is unique to the Army and to the military in general that you're maybe not going to run across when you're working on just like your standard commercial building project. The mission takes precedence, and if the mission can't be conducted because of a project, well, that project's not going to happen. That's just kind of the way it is in the Army. So we can ensure the mission is not disrupted, however, with energy resilience. And so I wanted to touch on what the definition of energy resilience is here, because resilience is going to pop up in this presentation and then just across, it pops up in my line of work a lot across the Army. So it's the ability to avoid, prepare for, minimize, adapt to, and recover from anticipated and unanticipated energy disruptions. Really, what that means in layman's terms is if the grid goes down, how can the Army respond? Are they going to be able to provide on-site energy? Is their mission going to be disrupted? Those kinds of things are very important to the Army. And because of that, there's a lot of policy and energy drivers that are focused on energy resilience in the Army. So these are a list of some of the top goals and requirements in the Army. I'm not going to read out or specify what everything is. There's different goals around renewable energy. There's a couple that touch on resilience and decarbonization. And just of note, we've been seeing a lot of electrification and greenhouse gas reductions goals over the past couple years in the Army. And then one thing to point out too, since we're getting a new administration this year, we do tend to see a lot of changes in some of these policies with an administration change. So these executive orders, that's what EO stands for down here in the decarbonization portion. Those are probably going to get repealed and changed with that new administration. So just something to be aware of, that administration changes do lead to different changes in the Army priorities. But right now we have the Army climate strategy, which has been really front and center in a lot of the work that I have been doing. We've been kind of hearing that, you know, the Army climate strategy is most likely going to go away or be rebranded with this new administration. So, you know, just keep that in mind. But this is a really interesting document that before I started work with the Army, I didn't know the Army was concerned about the climate. So I found this really interesting. It provides guidance and goals for the Army to be able to complete the mission while reducing the risk posed by climate change. So the Army is really recognizing these days that climate change does pose a risk to their installations. For example, hurricanes coming in and just demolishing bases, or tornadoes or flash floods. The Army has been pretty focused on, hey, how can we help reduce climate change so that our installations are not going to be as infected or impacted by the negative effects of climate change. And there's more goals in the Army climate strategy than what I have here, but I just wanted to touch on some key highlights that kind of have to do with greenhouse gas reductions. So per the Army climate strategy, they want to attain net zero greenhouse gas emissions from Army installations by 2045 and achieve a 50% reduction in greenhouse gas emissions from the Army buildings by 2032 from a 2005 baseline. Also, just of note, this isn't like a law. So the Army climate strategy is really just a goal that the Army has. It's something that they're working towards and that their leadership is prioritizing right now. All right, so getting into the meat of this presentation, I wanted to talk about ground source heat pumps in the Army. And given the resilience, decarbonization, and electrification goals, ground source heat pumps are really a great fit for the Army. And then I wanted to quick see in the chat what other names people know ground source heat pumps by. That is what I have been on a crusade to call them, is ground source heat pumps, but I know that there's many different names that this technology is known by. You know, for example, geothermal heat pumps. But in my line of work, whenever I hear geothermal, it can often get confused with geothermal electric. So that's why I strongly believe that they should be called ground source heat pumps. But I'd be curious what other names people know them by. And Max, when you have a couple answers.
Yeah, where would you classify geo exchange? I know that that was kind of a shift with some of the heat pump people to go with geo exchange. So it's more of like, no, we're just talking about closed loop in the earth and not
Yeah.
like popping into a volcano or whatever is kind of implied by like, the general public.
So in my experience, there's ground source heat pumps, there's direct use geothermal, and there's geothermal electric. And I really like to qualify the heat pump portion of it because in direct use, you're kind of going into some of those like thermal features to pump out hot water, um, which could be a geo exchange system. So, you know, I don't think that there's been any sort of like established guidance on the naming convention. This is just a personal preference, but that's how I personally feel about geo exchange. Is there's still some kind of room for misinterpretation with that one, I think.
I think so. And then another one to specify too is people are always wondering, like, are we talking about closed loop or open loop? And I know you have a slide about that
Right.
later, so that's another kind of key piece to narrowing it down, I think.
Definitely.
Yeah, but I'm getting a lot of geothermal and ground source in the comments.
Okay, great. So just a quick overview. I'm sure most of you are pretty familiar with what ground source heat pumps are. That's GSHP, as they're going to be referred to in the slide going forward. But I just wanted to give kind of a high level overview. If anybody has any questions, please feel free to drop them in the chat. So this technology provides both heating and cooling within one technology within that heat pump. Heat is extracted and rejected to the ground via a ground heat exchanger. And over here on the right is the different types of ground heat exchangers, which I'll get into in just a second. But really one of the key staples of ground source heat pump technology is that they take advantage of those stable ground temperatures to help increase efficiency, especially compared to air source heat pumps. Just 30 feet below the surface of the ground, those ground temperatures are really going to remain pretty much constant throughout the year. And so if you think of your temperature extremes, for example, in Montana, where I live, we'll have, 42 below as a low some days, but the ground is probably going to be 47 degrees. So it's significantly easier to extract heat to heat a home from 47 degrees than it is from 45 below. So that's a really cool feature of ground source heat pumps. And then, like I said, there's four main types. We have open loop, horizontal closed loop, vertical closed loop, and then pond loop, which you can see in the diagram over here. Unfortunately, this diagram didn't include an open loop system, but an open loop system is going to look really similar to that vertical collector. And then I just wanted to touch on pond loop a little bit. That's not something that I personally have seen a lot of, but it is something that I have seen gain interest in the Army recently. They've been kind of focusing on, hey, if we have a retention pond, is that pond potentially deep enough to put in a pond loop collector? So just something that I found kind of interesting in my line of work recently. And then just to touch on the components really quick here, let's see if I can, good. So this is the ground heat exchanger component. This is what, this would be a closed loop horizontal system with kind of a slinky layout. But this just really shows, it's buried in the ground. And then heat pumps, those are going to be located in your mechanical room. The scale, I would say, of this is maybe not totally accurate. Your heat pumps are probably not going to take up room, hopefully, unless they're big commercial systems. And then we've got the pump, which is going to circulate that fluid throughout the ground heat exchanger. And then if you have a water to water system where you're using water to heat and cool the building, you'd have another circulation pump there. Otherwise, you could have a fan system to circulate air through a water to air heat pump. All right, so some of the benefits of ground source heat pumps, some of these are going to be somewhat specific to the Army and to resilience goals. But they're an all-electric technology, and given the electrification goals that we've been seeing in the Army and then across the DoD in general, this is a really great option to electrify a traditionally fossil fuel end use. In net zero buildings and electrification, it's often very difficult to electrify that heating end use. And so this is one technology that you can really take advantage of to do that. It can be powered by on-site renewables in case of a grid outage. So if you do have on-site solar or even a generator, which a lot of military bases have, you can still provide heating and cooling to your building even if that grid goes down. So this is one of those resilience pieces. They're also one of the most efficient HVAC technologies out there. They can reduce energy consumption by 25 to as much as 50% compared to an air source heat pump. And then I did get a pre-submitted question about their efficiency, I think, compared to like more of a traditional HVAC system, like a furnace or a boiler. And I'll get into that a little bit more in the case study, but these really are like cream of the crop in terms of efficiency. This is going to be probably your best performing HVAC system in terms of efficiency, with COPs that range from 3 to 6. And then because they are more efficient, you're going to help with reducing the greenhouse gas emissions as well. And then another really cool resiliency piece of ground source heat pumps is that they're minimally impacted by extreme weather. So for example, if you have a hurricane that comes in and it just demolishes your building, well, hopefully that's not the case. But the component, the ground heat exchanger, is buried in the ground, and that system is probably going to weather that storm just fine. We've actually had some stories from resource efficiency managers, REMs, we call them, at installations, where they've had other systems just sustain some really bad damage from big storms, from hail, from lightning, and their ground source heat pump system continues to work. So that's really cool. And then they can also still provide heating and cooling during the extreme heating and cold events, like I mentioned, because of those stable ground temperatures. And then they're also extremely low in terms of operations and maintenance requirements. So compared to other types of HVAC, they have some of the lowest operations and maintenance requirements, which on military installations is really a boon because they often struggle to get financing for that kind of a thing. So just to give you an idea, the annual operating costs range from as little as $20 to about $200 per year, which is extremely low. But there are some barriers to installation for ground source heat pumps. One of the biggest ones that I hear is the high first costs. So these systems do tend to be pretty expensive. It's mainly due to that drilling and trenching requirements. That's where the vast majority of your costs are going to come from. But typically you can recoup those costs over the savings of the equipment that you're going to receive from the increased efficiency. And then there's also quite a bit of negative public perception out there, unfortunately. When ground source heat pumps were first kind of coming onto the market, they weren't designed super well, which led to a lot of systems not operating like they were supposed to. And this even still kind of happens to this day. So it's important to reverse those negative public perceptions when possible, because we really do have the technology and the experience now to install and design these systems properly. But you do have to have enough land to install a ground source heat pump. Different types of ground heat exchanger configurations require less land. For example, an open loop system is going to require less land than a closed loop horizontal system, but you still have to have the available land to install. And sometimes on military bases, you'll see, oh, there's this big open plot of land, but sometimes they're using that for like battle assembly or for ammunition practice. And so you can't put a ground heat exchanger out there, unfortunately. And then difficulty in receiving funding for projects. I know that this is probably common across any sort of sector, but in the military especially, there's a lot of competition for projects and not a lot of funding to go around, unfortunately. And this was something that I wanted to touch on, what makes a good ground source heat pump project. So what types of qualities are you looking for in an installation in a commercial building that is going to lend itself well to a ground source heat pump? So when we're looking at these types of systems, hopefully the heating and cooling loads are roughly balanced. This is going to help if they are the ground to not heat up or cool down over time. If you're constantly in cooling mode and rejecting heat to the ground, over time that ground is going to heat up, which can cause some performance issues. So if your heating and cooling loads are roughly balanced, that helps to kind of avoid that performance decline over time. And then, like I touched on, is there sufficient open space for ground heat exchangers and wells? I do have some rough rules of thumb for requirements, which can range for around 5,000 square feet for residential, all the way up to 43,000 square feet, which is about an acre for a district scale system. And then what's the geology in the top about 500 feet? The geology is going to play a key role in sizing your system. So we're really looking for the thermal conductivity to be high in the ground. That's what we want to see. We want to see good dense rock with high water content, and harder rock is also has good heat transfer characteristics, but it can sometimes be difficult to drill in, which can increase your drilling costs. And then a quick example of a less ideal geology is like some of those loose, unconsolidated sediments like sand. And then if we're looking at a building retrofit, it's easier, of course, to retrofit a system that's already used to working with water. So if the current HVAC system is hydronic, it's going to be a little bit more compatible with a ground source heat pump retrofit. And then, of course, does it pencil out? That's generally the bottom line for most projects. Is the system economic? And then I did get a pre-submitted question that I wanted to touch on here, that what is the maximum hot water supply temperature of a heat pump? So this is also important in a retrofit application. Heat pumps commercially available in the United States can get to about 140, maybe 160. There are some heat pumps that I have been told in Europe that can reach higher temperatures that are, I think, using ammonia as the refrigerant. But commercially available in the United States, you're really looking at a maximum hot water supply temperature of about 140 degrees. So if you're looking at a retrofit application, if your hot water supply temperature is 180 degrees, you're probably going to have to redesign your heating coils, replace those, or look at installing a supplemental boiler to bump up that hot water supply temperature when the temperatures outside are really cold. So getting into some ground source heat pumps installed in the Army. Unfortunately, I am only able to present on publicly available information, and there's not a lot of that available on how many ground source heat pumps are installed. There was a study done back in 1999, so this is not a current study, unfortunately, that said that there's over 7,500 systems installed in DoD facilities. So as you can imagine, there has definitely been more installed since then. But this is a much higher number than I was expecting to see. So DoD is making use of this technology. And then over here on the right, this is an example of the Army Corps of Engineers installing a ground source heat pump at Fort Hamilton that was done in 2011. And then some other key installations that are known for their ground source heat pump technology include Fort Johnson, Fort Knox, Fort Hunter Liggett, and Fort Hamilton. And then I'd be curious to hear in the chat if anybody else is familiar with other installations that have ground source heat pumps installed. So I'll pause there for just a sec.
So we got a couple comments that are related probably to a couple slides ago. Do you have any projects that you've worked on where the loop field was below a building or a parking lot, or is there any type of guidance that's like that is okay or that's not okay with the systems that you've mentioned?
Yeah, so I do. I'm actually working on a project for the GSA, General Services Administration, right now, where they're looking at installing ground source heat pumps in parking garages with a kind of novel, very small drilling rig. So that is, something that you can do. You can install them in parking lots, in parking garages, if you have enough clearance and the drill rig can fit. I don't think it's maybe as commonly done, but it's definitely something that we see done.
And then we had another one about soil contamination, but I would say this is, these are all going to be closed loops, but is there any sort of like brownfield avoidance or anything like that that would disqualify a project?
Yes, that's soil contamination is something you certainly want to look into before you start a project, like drill a test well and see what the soil is looking like. And sometimes the USGS Geological Survey, I think, will publish that information as well. In a closed loop system, you're probably not going to be worried about that contamination leaching into the system. But there can be issues with contamination during drilling where you have to mitigate. You don't want that contamination spreading because of your drilling and then the water that you're having to offput from that process. So that's really probably where that contamination issue would come into play, is in the drilling and trenching phase.
That makes sense.
Okay, are we ready to move on?
Yep, I think so. I'll keep an eye on other ones that are coming in.
Awesome. I wanted to touch on a couple projects that are ongoing right now. So this is the Federal Geothermal Partnership Initiative. It's otherwise known as the FedGeo. I'm not working on this project, but I do have a colleague that's working on this project. It provides technical assistance for the geothermal energy deployment at various federal sites, and it's a pretty new project. I think that they only have 2 ongoing sites right now, and then this year they're looking at doing a couple other partnerships, but the first 2 are Detroit Arsenal and then West Point, and PNNL, Pacific Northwest National Lab, is helping out doing the West Point evaluation, which is pretty cool. And I'm not going to read the quote, but there's that quote down there from the resource efficiency manager, the REM at Detroit Arsenal, where she's pretty pleased, it sounds like, with the potential of geothermal there at that site. And then this was just a study that was recently published. It was published by Pacific Northwest National Lab in collaboration with FEMP, which is the Federal Energy Management Program. DOE is the Department of Energy. So this was just published this fall. It was looking at ground source heat pump energy conservation measures, ECMs, that were implemented using DOE's ESPC IDIQ contract. Sorry for all the acronyms. The descriptions of those acronyms are in that text there. But the purpose of this was looking at audits that recommended ground source heat pumps as a measure, how many of them were implemented with this contract. ESPCs and energy service performance contracts, and UESCs, I think it's utility energy service contract. Those are really big funding mechanisms that we're seeing in the military trying to take advantage of right now. So they saw that there was 32 ESPC projects, which included ground source heat pump technology as an energy conservation measure. And then they also looked at some of the performance and cost metrics too. So energy savings they found were really well correlated with installed capacity, which I thought was interesting, and a good rule of thumb that you could use going forward in talking about ground source heat pumps. And then energy cost savings were averaging about $318 per ton, and total annual cost savings were averaging about $413 per ton. So this is publicly available. I'm happy to share it with anybody who is interested. And then I wanted to touch on 3 case studies in the military when I close out before I get into the case study that I did at my dad's house. So this is Fort Hunter Liggett. They installed ground source heat pumps in their single family housing. Originally, those houses had propane furnace with an electric AC for cooling, and there's 2-ton systems that were installed. So each house got its own individual ground source heat pump with the wells put in the front yard. And then during the summer, these ground source heat pumps could preheat the domestic hot water. So that's something that is seen somewhat commonly, is combining space heating with domestic hot water heating. And they saw with this system a significant decrease in the maintenance, and no electric upgrades were required. So that is another issue that I didn't touch on with electrification, is sometimes you're going to have electric upgrades that are required to be able to handle that increased capacity. But because ground source heat pumps are extremely efficient, oftentimes you're not having to do those electric upgrades because you're decreasing your demand in the process. And this is Fort McCoy. Fort Hunter Liggett, I'm going to mess this up. I want to say it's in California. Don't quote me on that. Fort McCoy is in Wisconsin. This is a commercial building. They installed the ground source heat pump in a 16,000 square foot commercial building with a water to air vertical closed loop. They had 55 tons of cooling, 42 tons of heating, and then they also had a backup natural gas boiler in case of failures, which is very common in the military. Again, with that resilience piece, you're often going to have backup equipment in case the first piece of equipment fails. But they coined this system as being highly efficient and resilient, and have been very pleased with its performance so far. And then the Army's kind of golden child of ground source heat pumps is Fort Knox. They've had really, really great success there. And they have installed quite a few different ground source heat pumps at that installation, but the most well-known one is the district heating and cooling system that was installed at the Disney Barracks complex. It's a vertical closed loop. There's 180 interconnected borer holes, which are about 500 feet deep, and they replaced some really inefficient central hot water boilers and various decentralized cooling equipment. And because of this project, Fort Knox was able to reduce its annual gas consumption by 10% with little to no increase in electricity consumption. So that's really just touching on the incredible efficiency of these ground source heat pumps. And then, of course, with that increased efficiency and energy savings, you're going to see a cost savings as well, which for Fort Knox was about $906,000 per year. And then they're also looking at installing a pond loop system right now in one of their new projects. So that's kind of a new novel technology that they're also looking into right now. So what are some of the lessons learned from these ground source heat pump projects in the Army, and just from my personal experience working, is that it's really important to work with experienced engineers and contractors. These are going to help make sure that your system is designed properly and that you don't have any issues down the road with the ground heating up or cooling down or installation. So really work with an experienced engineer and contractor. And then, how do you find these experienced engineers and contractors, you might ask? Well, the International Ground Source Heat Pump Association, they maintain a database for certified engineers and contractors. So you can get on their website and look through that database if you are in need of an engineer or a contractor. And then International Ground Source Heat Pump Association, they also provide some accreditations which are recognized nationally for ground source heat pump installation. And then I kind of touched on this, but it's really important to educate your stakeholders on the benefits of ground source heat pumps. So, this might be a little bit of a more expensive technology up front, but it's really going to help save energy on the long run. If you design it properly, it's going to be one of the most energy efficient heating and cooling systems that you can install in your building. So really educate those stakeholders so that your project can be successful. And then ensure the operations and maintenance staff receive, I have a typo there, proper funding, but proper training, but funding is required for training so that they can make sure that your systems are being operated and maintained so that you get the maximum life out of those systems. And then include measurement and verification plan and install monitoring sensors up front. In the military, you're required to do reporting on your energy systems, and we often see that that doesn't happen for ground source heat pumps because they don't have a measurement and verification plan during installation, and they're not installing the proper monitoring and sensors during the system installation. And this is really important to make sure that your system is functioning properly and as expected throughout its life. This is a really easy way to identify any issues and catch them before they become bigger problems. So here I've provided a couple of resources. And before I'm going to go back, I forgot about the pre-submitted question. What design issues impact overall efficiency? This is an important one. It's really well spacing. That is pretty much the biggest design consideration that you're going to need to take into account that can impact overall efficiency. If you're not properly spacing your wells and designing that ground heat exchanger properly, you're going to have issues heating up and cooling down the ground, and that's going to impact your efficiency down the road. So that's really the number one design consideration. And then some resources in case anybody needs them. There's an O&M best practices guide. I touched on the International Ground Source Heat Pump Association. They provide a ton of good data and really good information. There's also some information on what types of design tools that you can use on their website. And then Oak Ridge National Lab recently came out with a ground source heat pump screening tool, which is pretty cool. I think it's only a year or two old, and you can input your building's design parameters and I think your energy bills, and it will do a quick assessment of whether or not a ground source heat pump is going to be economic and a good choice for your building. And then the International Energy Agency has some recommendations for long-term performance and monitoring for ground source heat pumps. So this is going to really help you designing that M&V plan. Okay, finishing up today, we're going to touch on this case study that I did as part of my graduate research when I was in grad school at North Carolina State. I looked at the feasibility of combining an open loop ground source heat pump with solar thermal panels in a heating dominated climate. So like I mentioned, this is actually a system that my dad installed at his house. It was just kind of a wild idea that he had, and being a plumbing contractor with the right skills, he was able to install this himself, design and install it himself and with the help of people from his company. So that made it very easy for me to do a research project on, which was really cool. So this is a design diagram of what the system looks like. Unfortunately, I do have pictures of what it looks like installed, but I didn't include those today because there's a lot of components and they're spaced very far apart. But there's 4 solar thermal panels, which you see there on the right of your screen. I think they're Viessmann flat plate solar thermal panels. Those are connected to a big thermal storage tank, which is just a water storage tank. And funny story about that, my dad built that for my brother as like a little pool to jump in off the trampoline. And then once my brother was old enough to be out of the house, it got converted to a thermal storage tank. So that's the solar thermal heating portion. And then kind of in the bottom middle of your screen, you see the open loop wells. Those are connected to the thermal storage tank and the solar thermal panels by 3-way valves. So those 3-way valves are going to be automatically controlled to a temperature set point. The groundwater temperature in Bozeman is about 47 degrees Fahrenheit year round. And so anytime that thermal storage tank has a hotter temperature than the ground, so anytime it's greater than 47 degrees Fahrenheit, this system is going to be pulling heat from the thermal storage tank. Anytime the thermal storage tank gets depleted below 47 degrees Fahrenheit, those 3-way valves are going to switch and pull water from the open loop ground source heat pump. And then this system has 3 heat pumps. There is 2 space heating heat pumps, 1 and 2, and then there's also a domestic hot water heat pump 3. You got your various hydronic systems that you typically see, buffer tanks, pumps. And then since a boiler is what was originally used, that boiler was just left in as like a tertiary backup system. So the goals of this project were to compare the energy use of a modeled boiler with the energy use of a modeled combination system, and then also compare those modeled energy uses with the actual installed system, and predict and calculate the actual combination system energy savings. So the method that I used here was I designed an energy model of the home that was heated by a boiler using Carrier's HAP. I think it's Hourly Analysis Program is what that stands for. And then I designed an energy model of the home heated by the combination system using a combination of HAP and Excel. And then I measured the power consumption of the installed system using a well server data logging system. And I'll kind of breeze through some of this a little bit to get to the good part, which is the results. But this is just an example of the heat balance that I did on the thermal storage tank to create the Excel energy model. I used the hourly home loads that I got out of HAP as the input for that Excel program, and then I calculated the hourly input and output of the thermal storage tank, and then also the open loop ground source heat pump. So in terms of actually collecting data, like I said, we used a well server data logging system. We had temperature sensors and current switches, which determined if the equipment was on or off. We had power meters attached to all 3 heat pumps, and as well as we called it the pit pump. The pit pump is that pump that is in the open loop ground source heat pump. And then temperature sensors were placed at the inlet and outlet of all relevant equipment, and data was logged in 1 minute. I think that's actually wrong. I think it was logged in 15-minute intervals. So moral of the story is I had a lot of Excel data to work with, which was pretty fun. I did have a lot of issues, unfortunately, with data quality. So we put some power meters on each of the heat pumps, and heat pump 1 and heat pump 2, we had to basically disregard that data because you can see that there was some sort of electrical interference there. The heat pumps were never shown as turning off, which I knew that the heat pumps were off at periods of time. And so unfortunately, we weren't able to use some of that power meter data for heat pump 1 and heat pump 2, but we were able to use it for heat pump 3, which was the domestic hot water heat pump. And then, only about half of the sensors logged data. Unfortunately, I didn't have a tank temperature sensor in those early months. So, we got some of those sensors reinstalled, relogging. So I got good data from, about March to June. And then just kind of another fun fact about this system is that my stepmom was mowing the lawn and ran over the wire that attached the tank temperature sensor to the data collection device. So that kind of short circuited the whole system, and we didn't get any more data after June of about 2021. But some of the results that we did get, this is a weather comparison. So this study was done in 2021, which was an unusually warm year in Bozeman, and it had 4 of the 6 months with the same or warmer than average monthly temperatures. For the temperatures used in the model, I think I used the TMY3 weather data. But there was also more solar radiation available than was predicted in the model, so that's going to lead to more heating energy to that thermal storage tank. Looking at a comparison of the solar panel output, this was calculated based on the panel inlet and outlet temperatures recorded by well server with an assumed average flow rate of 2.2 gallons per minute through those solar thermal panels. And generally, the solar panel output that was predicted by the model was higher than that recorded by well server. So this is all just kind of reasons that there's going to be variance between the energy model and what was actually seen in the case study. The thermal storage tank is a parameter that I actually had really good success with. The tank temperature was predicted with pretty good accuracy, but the fluctuations of the actual tank were greater than what I was predicting in the model. The average temperature difference between minimum and maximum temperature was 9 degrees as measured by the well server, and I predicted it to be about 6.1 degrees in the model. But you can still see that that tank temperature was predicted with pretty good accuracy, which is really good because that's a very important parameter for the system. That tank temperature is really going to dictate whether or not you're using heat from the thermal storage tank or from the open loop ground source heat pump. Here's some COP results. COP is coefficient of performance. It fluctuated quite a bit more in the system than predicted by the energy model. And this is for just heat pump 3, I wanted to specify. I didn't get any measured data for heat pump 1 and heat pump 2 because of those data logging issues, unfortunately. But COP was generally over-predicted. You know, in general, you're generally going to predict that your system is operating more efficiently than it does in real life, unfortunately. And then this is the heat pump energy. So energy consumption was calculated by multiplying the work times the hours of operation. I didn't have any heat pump 1 or 3 hours in January or March because the loggers weren't working. But heat pump 1 and heat pump 2 work values were obtained from the model because of that corrupt data, like I mentioned. And then just kind of an interesting thing to touch on here, heat pump 3 work input, so that's the energy into the heat pump, was measured to be 4.2 kilowatts. But in the model, I predicted to only be a half a kilowatt. So that's a pretty big difference and discrepancy there, which is likely a trend that's going to carry over to heat pump 1 and heat pump 2. But of course, I don't actually know what those results are because the data loggers weren't working. This is just a quick comparison of the different pumps and the hours of operation. The main pumps that we were focusing on were the well pump, which is the ground source heat pump, the pit pump, which is that pump that pumps water out of the thermal storage tank, and then the solar pumps. And then, you know, another reason that I guess I didn't touch on earlier that we did this project, why we combined a solar thermal panels with a ground source heat pump, was to reduce that pumping energy for an open loop system. It can be pretty high for an open loop system since you're having to overcome that big height difference and it's not closed loop. So according to this analysis, there was about 310 kilowatt hours and about $36 saved in approximately 2 months of collecting data. So you're seeing some savings there from installing those solar thermal panels, but not anything too significant. And then quick, the boiler energy, I think that the model didn't predict a lot of boilers energy consumption, but we did see the boilers turning on throughout the year. And then this is the good stuff. So this shows the comparison of the baseline model, which is the boiler. And I did have energy bills to calibrate that model too. So it's a good representation of what the house was using before the system was installed. And then the prediction of the energy model and the well server data. So the energy model predicted an annual energy savings of about 24,900 kilowatt hours per year, but the system would cost $288 per year more to operate than a traditional boiler. And one of the reasons for this is because the price of electricity is double that of propane. So unfortunately, there's not a lot of incentive to switch to an all electric technology, at least at the time of this study, because the cost of propane was so cheap. And the energy model overpredicted the energy consumption by a factor of about 1.6 and overpredicted operating costs by a factor of about 1.7 during that measurement period from April to June. So if that trend is applied to an annual consumption, the combination ground source heat pump and solar thermal panels could save about 32,500 kilowatt hours per year and about $917 per year compared to a traditional propane boiler. And then these are just some results discussions. So period of comparison. I touched on most of this in the last slide, but the key takeaway really is going to be that yes, the system is going to save you energy if you install a similar system. You are going to see savings from installing those solar thermal panels compared to just operating an open loop ground source heat pump. And I did not do a economic analysis on this project. Unfortunately, I didn't have time to do that. Just where it fell in my graduate research, I didn't have the time to complete that analysis, unfortunately. But these savings that we're seeing are not super significant. So though it's a really cool system and it was really fun to research, economically, it's more than likely not going to pan out. And that is going to conclude the case study presentation today. So this is kind of a review of heat pumps in military applications with some follow-on questions. And I think we'll open it up for questions now.
So we got a lot of questions, and a couple of the things. One, as just like I think a terminology thing back to the beginning, there was a comment about bores versus wells. Is that something that do you want to kind of go through like the difference there? I said in the comments that I feel like that's a drill rig hangover more than like every hole in the ground is not necessarily a well.
I have not gotten into too many discussions about this. In my mind, a well is an open loop system. So that's like something that you're actually pulling water out of, a domestic water well, an open loop well. A borehole, in my mind, is something that's a closed loop system that you're going to be putting a pipe in.
No, go ahead.
So I was just going to say that I don't know that anybody like is necessarily going to call you on that. I've never heard any like specific terminology and any sort of like standard, but
Yeah.
that's how it is in my mind.
And there was kind of a related comment too, and you mentioned this as far as like a test bore to see what in the kind of the context of a brownfield or something like that for contamination. But have you had projects that were a no-go because just the ground was not going to be it wasn't going to have the conductivity that you were looking for versus just like, okay, this is just pure granite under this house. So this is very different from some like loose sand that we found at a different application on an island or something.
Yeah, I personally have not had experience with projects like that, but I've talked to people that have. It tends to be more of an economic thing, right? For the most part, you can install a ground source heat pump anywhere. It's really just a matter of how much piping you're going to have to put in the ground. So if you have a low thermal conductivity, some of those looser sediments, you're going to have a bigger ground heat exchanger, which is going to increase your costs. So, you're likely going to have a more feasible system in an air source heat pump or a furnace or something like that. And then conversely, if you're getting into drilling some of those really hard rocks, while they're very good for thermal conductivity, again, that's going to increase your cost and it's just not worth it to some people.
Yeah. No, those are good points. And that's something that can be, like you mentioned, modeled. And I think that we have some IGSPA, which is my favorite acronym.
Yep.
And put people onto. And there are some of those things that with a test bore, you could see if that's like worth drilling 100 holes or if like, okay, maybe we should reassess here. And I think that there's also just like some almost local just knowledge of the ground that like the drillers are gonna be like, yeah, there's no way I'm gonna give you a good price for that. And that one of the issues when I worked in Chicago is it just was super expensive to drill in Illinois. for whatever reason. And then just like in Missouri or whatever, it wasn't, and that was just a local consideration that was different. That was kind of beyond just the math penciling out based on like what was actually below you. Um, there was a question, I've never heard this term before. Have you heard of like a conical loop field? I don't even know.
I have
I
not heard of a
that looks like an
conical
ice
loop
cream
field.
cone. Um, but
Interesting.
yeah,
No, I haven't heard of that one. I have been seeing, I do have a project that I'm working on at work right now, for an inclined well field. So whereas opposed to going straight down, you're kind of drilling at angles. So theoretically, you don't need as much space. But I have not heard of the conical. I'll look into that.
that's a good one too. Just kind of like a directional bore, like you'd go under a street or something like that. It's kind of an
Yep,
interesting. I mean, they seem to be great at that with oil and gas to snake down under the earth and find
right.
the pockets of natural gas or whatever. So, okay, the one of the other questions I had, are any of these tied to a bigger like district energy system? Are these mostly building specific, that the systems that you mentioned, the case studies?
That Fort Knox system was a district scale system. I don't know that there's too many more specifically in the Army that are district scale. I tend to see a lot more of like building level systems, but that might just be because of what I have worked on. Not
Yeah,
necessarily that the district scale are less popular, but they require a lot of space too.
yeah, and as mentioned, the sometimes those just like aren't public knowledge. They're probably of the like what did you say, 7,500 projects, and I'm aware
Right,
of the ones that you mentioned, a couple that I know of in Colorado, and then we got like 3 or 4 additional sites in the chat that were mentioned.
right.
So yeah, it seems like it's a good fit for this. I think just to mention that a big loop field with a bunch of buildings pulling off of it in a campus scenario seems like a good fit for a military base,
Definitely. Yep.
um, for an installation. The one of the questions was, some projects that one of the viewers has worked on, just like with the Department of Defense, that initial first cost is kind of a barrier. I think that your Fort Knox case study was a really good return on investment calculation. If you had to just had an elevator pitch with the Department of Defense for an installation, what's like the best case study that you think you'd lean on to say this is proof that it is more expensive upfront, but like this is why it can be a home run?
Fort Knox. I mean, that's just everyone knows it.
Yeah,
They've had the best success there. Um, it's the most well known. It would be interesting. There just also hasn't been a lot of other case studies actually done on, like those two others that I pointed out, Fort Hunter Liggett and Fort McCoy. They weren't full blown case studies. They were just kind of like, oh, they have them installed and they're generally happy with them. So yeah, I think Fort Knox is probably going to be, at least in the Army, your best bet.
yeah. For these evaluations of return on investment, is it you kind of described a set of at your dad's house, a set of sensors that you put together with voltmeters basically to see what the usage was for the electricity. Are there any of these sites that use like BTU meters that have a flow meter and then like a delta that they measure, that they kind of do the calculation, or is this more custom?
Um, I I don't know, I guess. I don't think so, to my understanding, just based on some of the information that I've seen lately. They really don't have a lot of measurements that they're doing on these ground source heat pumps at all. People are very familiar with electricity meters and electricity submeters,
Yeah,
so they're easy to install those. But then when it comes to, like you say, the BTU meters where you're needing flow and temperature and difference between the two sides, um, a lot of these REMs at facilities are really overworked, and that's not going to be their priority, unfortunately, to go pull that data for reporting or measurement and verification.
so just kind of the utility bill is
Yeah.
probably most of the ROI calculation there.
Yep.
Yeah. One of the questions that somehow comes up in every webinar that we do, is there like a refrigerant of preference with these projects that you've worked on, that like, okay, these installations are moving away from this refrigerant because of this new refrigerant that they prefer, or is that still kind of case by case that you decide if like, okay, we want to use propane, we're moving to this, or we're moving away from that? Is that part of the discussion, or is that project specific?
It's project specific. And again, that's probably going to change with this administration. Whereas, we're like, oh, maybe we should get away from using coal, right? And like dirty grids and stuff. That's been a focus of our work recently. That might be changing in the future. In terms of specific refrigerants, I have not encountered um, any sort of requests for a specific refrigerant in my work.
Okay, yeah, I think that that's just like an industry question. Everybody's looking for guidance to
Yeah,
say that, hey, the Army is moving away from this or moving to this would be
right,
good to know for whatever
right.
reasons. But yeah, I think that just like the bigger context of this presentation is important though, because as you mentioned, just like with administration changes and the preference for the energy type, just being energy efficient is so important for everybody that that's
Yes,
like the
and
we
that
are there.
that doesn't go away either, right? Like with the administration change is, the focus might shift off of electrification and more onto cost savings, but energy efficiency saves you money at the end of the day. And so that's still going to be important no matter who's in office.
Yeah, yeah, just having a few different fuel choices to use in case there is some sort of interruption with the grid or whatever, that just switching back to all coal all the time probably doesn't
Yep.
help with these resiliency goals. If everything at the installation is just like plugged into the outlet down the street or whatever, that
Yes.
probably isn't safe enough. One of the other things that I had heard from a base in the past, they liked Geo because there's not like, you can't just put a bunch of propane tanks next to like barracks for an installation just for safety reasons. So that was a big advantage too, that really everything is contained and there aren't just like big piles of gas and tanks like all over the place, which would be an issue
Yes.
for a variety of reasons. Is that part of the assessment too? Just kind of like, is there a safety piece that is a push towards geo in that case?
We're not really designing these systems, so we're more, looking at feasibility and case studies and stuff like that. So I haven't seen it, but I can't imagine that safety is not a consideration. And to your point, if you're not allowed to put propane tanks next to barracks, then what the heck else are you going to put there? Well,
Yeah, or
might as
yeah,
well put a ground source heat pump.
yeah, you're gonna have to like walk over what could have been a ground source heat pump to put that tank more remote and
Yeah.
safely away or whatever. So okay, let's see. Just looking through some of the other. There were some other questions about just like sizing pumps versus circulators, which is a bigger hydronics question that comes up all the time. It's almost another like nomenclature thing that for closed loop, we're talking about circulators, and those would be closer to some sort of hydronic circulator that you would use even if you didn't have geo. And that sizing by like the pump or by the pipe manufacturer is probably easier. Do you have any recommendations for like open loop pump technology where actually like pump and dump moving water, like pumping it, not just circulating it? That's kind of a tricky question that I just asked. Is there like
Yeah.
pump technology that is a better fit for these projects? I don't know if that might be case specific. That was just one of the ones that was in the chat.
Yeah, I mean, it's a good question. I don't really do a lot of designing, so I don't know that I'm going to have the best answer for that. With the open loop system at my dad's house, it's a submersible well pump. Um,
Okay.
so that's what they use there.
Yep. So starting there, and one of the things I put in the chat is just like it also really depends on how dirty that water is too.
Yes,
I guess if you're talking about like really warm but muddy water from something, that could be an issue. So
definitely.
okay, well I think that um, we've got a couple other questions that we'll follow up with offline. So thanks for everyone for attending. If you want to do the last two slides,
Oh, yeah.
I'll show the contact info. So
Nice.
thank you. And I think you were going to say that. Thank you. Here's our tech support team. If you've got any project questions, you can reach out to us by phone or email. We'll answer the phone, or we go through a lot of emails to that tech support line as well. And then, as always, we love to see your project. So if you want to tag us on social media or send me an email or however you want to get that across, we love doing project specific webinars like this where we can talk about a system that's not theoretical but is in somebody's dad's house or whatever. So with that, I think that we'll wrap it up there. Thank you so much for joining. That was really helpful, and I think bridges a gap with that sustainability and resiliency thing that we're like really talking about a very similar mechanical system that is important for a lot of criteria, especially in these military installations that it's really not political. This is like something that
Yes.
is the best system for the task, and I think this technology could really scale into the million other civilian things that would have a similar way to assess a new building's energy needs. So, yeah, anything else to wrap up with?
No, just thanks everyone who attended today. I'll thank you, Max, for having me. It was a pleasure to make this happen, and it's
Yeah,
been a lot of fun. I've really enjoyed presenting today.
yeah, absolutely. Thank you so much. All right, everybody, we will see you. We're going to take January off because of AHR, so we'll get information out to everybody for our February webinar. Thanks so much. Have a great end of your year. Happy holidays. And thanks again to Nicole.
Thanks.